Greetings of the day, dear students. In this video, we are going to discuss about the regulation and efficiency of a transformer. We will discuss the important formula for percentage regulation V2 naught minus V2 full load divided by V2 full load into 100, and also we will see the percentage regulation in terms of resistance, reactance and power factor, cos phi and sin phi, right? And when to use the positive sign and when to use the negative sign. And also we will discuss the efficiency of the transformer, how to calculate, how to express in terms of either in input or either in terms of output, and what could be the condition for maximum efficiency. And also we will see all day efficiency, and we will discuss one example how to calculate in detail, how to calculate the efficiency losses and the percentage of regulation. All those things we will discuss in this video, right? Dear students, what happens is, with respect to the transformer, one second, yeah, as and when the transformer is loaded, the secondary terminal voltage, the secondary side terminal voltage changes with the change in load, and this is due to the, with respect to the change in load, the amount of current drawn by the load will change, and because of that there will be some voltage drop across the winding resistance and leakage reactances. Now because of this voltage drop, there will be the change in voltage across the secondary of the transformer from no load condition to the full load condition. Now that change, if it is expressed in terms of full load and multiplied with 100, it gives you the percentage regulation of voltage. Percentage regulation of voltage. How do you understand that? For example, without any load, if the secondary is showing you the voltage of 220 volts, now you have fully applied the load on the secondary of the transformer and it is drawing full load current. At that point, if the voltage came down to 180 volts, then what is the change? 220 minus 180, it is around 40 volts divided by 220. So 40 divided by 220 expressed in percentage, 18.18. So 18.18 percentage of voltage change is there from no load to full load. Now the next question arises whether this value should be high or low. For example, if two transformers are given, one transformer is having regulation voltage as 3% and the another transformer B is having voltage regulation as 3%, which transformer is to be preferred? Yeah, the transformer which is having low voltage regulation, that the transformer is to be preferred. So for an ideal transformer, this value should be as much low as possible. So if it is 0%, perfect. So how do you understand that? Even though there is load, full load or no load, there is no change in the voltage across the secondary of the transformer. Constant voltage is maintained, but practically it is not possible. Definitely there will be some change in voltage, right? Now how do we calculate that? Observe, in this formula, V2 naught minus V2 full load divided by V2 full load, V2 naught represents the secondary voltage when the load is thrown off. Thrown off in the sense when there is no load, when there is no load. So V2 full load represents the full load secondary voltage, and it is assumed to be the adjusted to the rated secondary voltage. Now for the ideal transformer, the voltage regulation is 0. So its meaning is there is no change in the secondary voltage from no load to full load, right? So we also know that V2 naught minus V2 is equal to I2 times bracket of R naught to cos phi plus or minus X naught to sin phi. So if it is lagging power factor, if the load connected on the transformer is of lagging in nature, lagging load, then we have to use the positive sign. If the load is leading in nature, then we have to use the negative sign, right? So here R naught 2 and X naught 2, if you further simplify that, I2 R naught 2 divided by V2 cos phi plus or minus I2 X naught 2 divided by V2 sin phi into 100. Now this value represents R per unit, and I2 X naught 2 by V2 represents the reactance value in per unit. So X R per unit and X per unit. Now phi represents the power factor angle. Phi represents what? Phi represents the power factor angle. Now the regulation will be maximum when the phi is equals to the tan inverse of x naught 2 by r naught 2, and it occurs if it occurs at the lagging power factor, right? This formula is important. Now what about efficiency? Number of times we have discussed, it represents the output power by input power, but our input is nothing but it is some part is of some part of the input will be available as output, and remaining is lost in the form of losses. And those losses we already know, copper losses and iron losses. So we can write it as output by output plus copper loss plus iron loss. Or in another manner, our output is nothing but input minus losses. Whatever the output is available, that is nothing but the input minus losses. Input minus losses by input. This is also okay. Either of these formulas can be used depending upon the data given to calculate the losses. To calculate the efficiency of the transformer. Now we can find out the copper losses from short circuit test, that is what we call the SC test, and we can find out the iron losses from open circuit test, that is what we call it as OC test, right? So using those two tests we can calculate the copper loss and sorry, iron loss. Now what could be the condition for maximum efficiency? At what point or at what instant the efficiency will be maximum? So for that sake, what we have to do is efficiency equals to output by input, nothing but input minus losses by input, but the input is Vi cos phi minus losses are I1 square, I square are copper losses, and the iron losses which are constant Wi, whole divided by input Vi cos phi. Cos phi represents the cosine of the angle between V and I. The same thing can also be written as, if you further simplify, V1 I1 cos phi divided by V1 I1 cos phi, it is 1 minus I1 get cancelled, this I1 get cancelled, so I1 R naught 1 divided by V1 cos phi 1 minus iron losses divided by V1 I1 cos phi 1. Now all these things are variable with respect to the amount of load we apply. So what we do here is, for example, we have to differentiate that value with respect to the current and make it equal to 0. This point is very important. In this equation, we have to take its derivative with respect to which variable. Here so many variables are there. I1 is there, R01 is there, V1 is there. So out of all these things, we will do the derivative with respect to the change in current with respect to the I1 and simply make it equal to the 0. Then that leads to the condition of the maximum efficiency. So here I1 square R naught 1 is the copper loss represented with variable WCU, power loss in watts WCU. Wi, iron or core loss, is nothing but hysteresis loss plus eddy current losses. Our iron losses is nothing but sum of these two, hysteresis loss and eddy current loss, right? Now derivative of this efficiency with respect to the I1, the first value is constant 0, derivative of constant is 0, minus R naught 1 divided by V1 cos phi 1 plus Wi divided by V1 I1 square cos phi equals to 0. So if you further simplify, R naught 1 divided by V1 cos phi 1 equals to V1 Wi iron losses divided by V1 I1 square cos phi 1, V1 cos phi 1 will get cancelled. So indirectly Wi, if Wi value is equal to I1 square R naught 1, so but I1 square R naught 1 represents what? Copper loss. So indirectly, if iron losses is equal to the copper loss, then at that time the efficiency of the transformer will be maximum, will be maximum. This is very very important. The point at what instant these iron losses are equal to the copper losses, at that instant the efficiency of the transformer will be maximum. So indirectly the amount of current I2 will be equals to the root over Wi divided by R naught 2. The efficiency will be the maximum. Now what about all day efficiency? Output of the transformer in kilowatt hour in 24 hours whole divided by input of the transformer in kilowatt hour in 24 hours will give us the all day efficiency. So iron losses are constant and those are present during all the 24 hours, but copper losses will be varying depending upon the current drawn by the load from hour to hour, right? So in this context copper losses are variable, iron losses are constant, right? Now we will discuss one example how to calculate the efficiency of the transformer at half load, right? We will discuss this example. A 220 volt, a 200 by 400 volt single phase 50H 10 kVA transformer has at full load copper loss of 120 watt, and if it has an efficiency of 98% at full load, unity power factor, determine the iron losses, and also what will be the efficiency of transformer at half load and 0.8 power factor lagging. So dear students, number of times I am repeating the same point. Whenever the problem is given, please identify the given data with proper variable names, right? So in this context he has already given you this is the primary voltage and this is the secondary voltage. We have specified 200 by 400 volt. So the primary voltage V1 is the variable we have to use is V1, that is 200 volt, and the secondary voltage the variable we have to use is V2 equal to 400 volt, and we have specified single phase transformer and the operating frequency is 50 Hz, right? Now the power rating is also given. The power rating or the output is given as 10 kVA. How do you understand that? It is equals to the power output V2 I2, right? 10 into 10 power 3 volt amperes. Now what about the efficiency? He has already specified 98%. So output by input equals to 98%, that is equals to the 0.98, right? But already we know that efficiency equals to output by input, nothing but input minus total losses by input, or output by output plus total losses. Here in this context the total losses meaning is both iron plus copper loss. Now the operating power factor cos phi is given as unity, so cos phi equal to 1. Now the full load copper loss, the full load copper loss PCU will be equals to the I2 square R naught 2, that is also same as I1 square R naught 1, right, which is already given. It is equals to 120 watt. Now what will be the input power? Simply output by efficiency. So output already we know the rating of the transformer 10 kVA, 10 into 10 power 3 divided by efficiency already given 0.98. Based on that we can say that the input power is 10.204 kilowatt, right? So once we know the input power, which is nothing but output plus total losses, so here our total losses, which is the combination of both copper and iron losses, will be equals to the input power minus output power. So input just now we have calculated 10.204 kilowatt minus the output is 10 kVA, 10 into 10 power 3, right? And the power factor is unity. So 10 kilowatt is the output, right? So 204 watts is the total amount of loss. 204 watts are the total losses, but this total losses is going to constitute both iron and copper loss, iron and copper loss, right? Now if you observe our iron losses we can separate at full load, whether it is full load or no load or off load, the iron losses will be constant, right? So here Iron losses equal to total loss minus copper loss. Copper loss I square R, it is already given. So once we know the total loss minus copper loss, which gives us the iron loss, which is nothing but 84 watts. 84 watt is the iron loss. Now at half of the load, and at operating power factor 0.8 cos phi equals to 0.8, what could be the losses? Copper loss at half load will be equals to the I by 2 square into 120, which is nothing but 30 watts, but iron losses remains constant, 84 watt. So the total losses at offload and 0.8 power factor will be 30 plus 84, which is equals to the 114 watt. Now output at half of the load and at 0.8 power factor will be 10 kVA divided by 10 kVA divided by 2 into power factor is 0.8 into cos phi. So the output power is only simply 4 kilowatt. 10 into 10 cube by 2 into 0.8, we will get it as 4 kilowatt. Now sorry, now the efficiency, output by input, nothing but output by output plus losses. So output is 4 into 10 cube divided by 4 into 10 cube plus the losses 114 watt equals to 0.97. So this is the efficiency of the transformer at half load and zero point 0.8 power factor. So dear students, in this entire discussion, the very important points are the efficiency of the transformer, regulation of the transformer, the percentage change in voltage from no load to full load with respect to the full load into 100 will give us the percentage regulation. The regulation value should be as much low as possible. If two transformers having one transformer is having 18% regulation and the other transformer having 3% regulation, then we are going to prefer the transformer which is having low regulation. Ideal case is 0%. Its meaning is there won't be any change in the voltage from no load to full load across the terminals of the secondary, right? So practically it is not possible. And regulation in terms of resistance and reactance, I2 bracket of R0 to cos phi plus or minus X0 to sin phi divided by V2, positive sign for lagging power factor and negative sign for leading power factor. And another important condition, the efficiency of the transformer will be maximum if the iron losses are equals to the copper losses. At that point of time, the efficiency of the transformer will be maximum, and the all day efficiency of the transformer, output of the transformer in kilowatt hour in 24 hours divided by input of the transformer in kilowatt hour in 24 hours, right? And also we have seen the example. So this is what all about the regulation and efficiency of a transformer, right? Thank you.